We can now continue with the second speaker before we have a break, and it's really my great pleasure to introduce Dr. Murat Tanik. He will deliver the commemorative lecture on the general theory of relativity. Sorry about this. General theory of relativity, first introduced by Albert Einstein in 1915. Professor Tanik's lecture will focus on common thread running through a group of mathematically disparate and widely accepted scientific theories composed of general relativity, the second law of thermodynamics, and the quantum electrodynamics of Feynman. The communication channel formalism introduced by Shannon is considered to be a heuristic connection. As an internationally respected and accomplished scientist who has dedicated his life to SDPS for over 21 years, we are honored to announce the Albert Einstein commemorative lecture celebrating the 100th years of general relativity theory by Professor Murat Tanik. Please welcome Professor Murat Tanik.
Bernd, you surprised me. You should have told me this part of your presentation. You know, I prepared a very short 3-hour presentation for today. When I see Bernd's presentation, I said, you know, maybe I should add just another hour on it, so it's going to be 4 hours. First, Oscar gave a very nice summary of quantum computing, quantum information theory. And then when I listened to him, I said, see, this adds another 15 minutes to the talk, okay? So, and then Vladik, last night, entertained everybody in such a short time, giving very beautiful summary of quantum effects. So that adds another 15 minutes. So now we are 4 hours and a half kind of this time. Before I start, let me connect to Petri first. You know, you already figured out from my accent that I'm from Texas. You know, that's my common line. Although I was born in Turkey and come to the United States in 1970. 75, my professor, I was already working in NASA Research Center at Texas A&M University. And the research center was connected to DARPANET. We were in today's internet already, experimental internet. The computer I have had another box bigger than this, a computer connecting to the internet of the time, which is DARPA. Later became ARPANET and all that. My professor told me that your research project is to prevent deadlock in large networks. Deadlock detection and timeouts and stuff already kind of solved. But prevention is because in a large network, when people talk to each other, it can deadlock. Deadlock is essentially something like this. You go to a grocery store, if the salesman is a computer, you purchase this, you say, I want to buy this. The salesman says, pay first. You say, no, I want to get this first, I don't trust you. He says, pay first. So with deadlock, you know, he wants me to pay first, I want to get my thing first. So we never resolve. Since we are human, we just go there, put it there, then pay the money later or take later. But the computers are not like that. It has to be very precise. Therefore, the deadlock problem occurs. Then, connection to Petri. He said that these are the books, technical reports from MIT about Petri nets. This should be your starting point. So he gave me 3-volume MIT technical reports on Petronets. So that was my starting point of my dissertation in 1975. And 78, I finished. I named this talk Adventures of Reluctant Computer Guy because 1967, I listened to a Turkish American come to my university, Turkey. He gave a talk about finite element analysis, using computers to solve complex problems. I said, oh my God, computers. You know, such important stuff. I thought, I knew about computers. We have some IBM 1620 in our university. Later, we got 36040. I have some idea about computers, but I didn't know can do all these big problems. I said, I have to learn about these computers. I went to my department chairman. You know, I want to study computers. You know, in those days, we were small departments. They could schedule your program accordingly. So he scheduled me a computer study program. And I started taking courses, of course, electrical engineering, standard courses, and mathematics courses. I took 4 logic courses, logic 1, logic 2, logic 3, logic 4, because of that. And then I also want to learn about the biological aspects of computing because I realized there was a book in the library, very few books about computers. That book was in German. I knew little German. The name of the book was Mensch und Maschine. And that gave me the perspective that only way to understand computers, you have to study electrical aspects of it, mathematical aspects of it, and the biological aspects of it. I didn't know about computing, which covers many things, but I was thinking computers, which in 3 aspects of it. So I figured that in 67, 68, I have to build a computer to understand. After I formed a computer club, and you know what? We built AND gate and OR gate. Just a couple of lights, and then you turn it on this way, this way, the lights comes up or don't come up, something like that. AND OR gate, I'm not going to explain AND OR gate for people who may not know. That was the, I thought, preliminary computer design. We couldn't do anything, in other words. When I come to the United States, in the 70s, after a couple of years, like I said, with the Petronet, we start working on. So my motivation, which I'm going to end up with Einstein, motivation has never been involved physics. I don't understand physics. I never did. And in those days, I avoid from physics because it didn't make sense to me. You know, mathematics was more precise. Computing was precise. It makes sense. Physics, bunch of assumptions and this. And electronics course was the worst one. Bunch of diagrams. This is the device. It gives you these parameters. Where does it come from? It's just all from empirical stuff. Didn't make sense. And Einstein was the worst one. I'd never believed it. All the way to 80s. My son asked me, can you explain relativity theory to me? I told him, I cannot, because I don't know, and I don't believe it really, that stuff, because it doesn't make sense. You know, some guy having a clock, this is the way textbooks say. A guy has a clock. He has a twin. One of them flies away with the clock. And that clock slows down and stuff. Even, do you think it makes sense? No, I couldn't convince myself to the mathematics and to the concepts. So I said, you know, although it's written somewhere, this kind of stuff, just forget it. You know, we don't use it anyway, I'm thinking, forget it. But eventually, I end up trying to build a computer, end up there, and I'll show you how, okay? That's why I named it Adventures of a Reluctant Computer Guy, because I never intended to go that way, reluctant. 67, 2017, I put here. The reason is, next year I will visit various friends to get into the more details of today's talk and the applications. We're working on the applications of the talk I'm going to give. And 2017, it will be the 50th year starting to design a computer, which I think, finally, I understand what a computer is. All right, next slide. This is our workplace in UAB. You know, essentially, it's a nice place. Birmingham is a nice place. Steve called me. I was in University of Texas. Dr. Steve Rigenda called me one day about 10 years ago. He says, you want to come to Birmingham? I said, Birmingham? What am I supposed to be doing in Birmingham? He says, such a beautiful place. Everybody says hi to each other, beautiful weather and everything. So I visit, and I end up in Birmingham a little more than 10 years now. It's a beautiful place. You're all welcome to visit with me. I promise I'll show you around, and you'll enjoy it. Since nobody expects much from Alabama, you know, it's a small state. If you look at the statistics, not a rich state, one of the poorest ones. So our tradition is to exceed the expectations. It's easy because we don't expect much, so I can exceed the expectations easily in our place. This is some of the presentation, some of the papers, you know, that I write. This presentation is based on. I have never given this talk before. This is the first time I'm giving, and I chose this avenue because SDPS is our baby, and I hope that this talk will be an important one. So this is the first time I'm talking about this. I never talked before. However, under certain disguises in different aspects of the theory, I published here and there. Then why you should do disguise or anything? Well, the point is that, you know, if you're familiar with Thomas Kuhn is a American philosopher. He has a concept, he says, paradigm shifting ideas and the normal science. All of us do normal science for survival. Normal science is we accept the existing paradigms, we push it here and there. Most of the Nobel Prizes are normal science. I mean, very few is paradigm shifting science. Paradigm shifting in the term of Thomas Kuhn is changes the way that we think. It doesn't come easy. It has to be luck. It has to be chance. Luck and chance, kind of. It has to be opportunities, mix of ideas, some craziness, something. We don't know, but that's what paradigm shifting is. It changes the way we do things. What kind of things paradigm shifting is? Copernican revolution, you know? That sort of thing that Thomas Kuhn talks about paradigm shifting. You won't get grants with paradigm shifting ideas. Your papers won't be accepted, I guarantee you, paradigm shifting ideas, because all scientists, me included, buried in our everyday lives, we judge each other based on the everyday things, you know, practical things. Therefore, my day job is to design complex software, computer systems. I work in F22 design. I work on battle management systems, things like that. That's the day job. That's where the support and recognition, money comes from. But as a hobby, you have to do something interesting. And this is my hobby, last 50 years. So these are the doctoral dissertations. You know, I have about 25, 30, something like that, doctoral dissertations. And some of them master's thesis, about another 40 something. I gave sometimes some of these topics in some narrow band to some students who are interested. I gave Cengiz, I think if he's here, yeah, Cengiz, this problem. Enqui's problem and its applications to computer science in 1992. He came, I was at Southern Methodist University after Dr. Ye's, working for Dr. Ye's company. You know, 40 years old, I thought that it's time to go to academics, finish the book that I was writing, which I finished 1991. So Cengiz came. I gave a talk in Turkey about battle management systems, the normal science stuff. And they were impressed. So one student came to me, Dr. Tanik, I want to work with you. I have a scholarship, can we do it? So he came to SMU. He was the #1 guy in his college. So I said, Cengiz, I'm going to give you my #1 problem, really good one. He says, I'm going to mention to you Anquin's problem. I want you to do your thesis with Anquin's problem. Anquin's problem is very simple. A chessboard, 8 by 8, let's say. You put queens in a way, they won't attack each other. So you can put a queen here, queen here, queen here. If we remember how the coins go, they won't attack each other. So that's the solution for an Anquin's problem. By the way, from the mathematical point of view, still an unsolved problem. Unsolved in the sense that n by n queens, number of solutions for n by n queens not known yet. There is no formula. So I told him, I'll give you n queens problem, but we're going to study not the mathematical aspects of it, some applications or something. He took it. 3 months later, he never come back to me. I saw him in the hallways one day. Cengiz, what is going on with the n queens problem? He was like, this is Professor Tanik. I have to tell you something. I say, what's it? He says, I solved that problem already. I say, really? Yes. Our teacher asked as a computer programming. I wrote a computer program for the Anquin's problem, and I solved it. So I don't understand why you give me this master's thesis for Anquin's problem. It's a joke. So he was thinking that I don't understand things. He was so apologetic. He knows so much about Anquin's problem. I said, Cengiz, come, I'll show you something. I took him to three file cabinet, 3 layers. I said, come. I pulled one file cabinet. I show a bunch of papers and the notes and documents. I say, these are about Anquin's problem. You see this one? You see this bunch of notes that I take and other papers, which doesn't look totally unrelated. Circuit theory books, biology, all kinds of stuff. And then pull the other one. I say, these are the projects we did, and these are the other things. So I'm asking you to study these things and somehow put together. I'll help you. I'll give you the notes and stuff. And I said, Cengiz, if you do this thesis, you'll be famous. He walked away, and then he finished in 1992 his master's thesis in Anquin's problem. 10, 15 years later, I got a phone call. He was working in River Systems. He actually involved in designing the Sojourner Mars lander, okay, the real-time systems, So he called me, Dr. Tanik, you told me if I study Anquin's problem, I'll be famous. He says, yeah. He said, I'm famous now. I said, how come? He says, go to the web, the Wolfram website. There are 8 papers listed there about Anquins. Anquins publish hundreds of, maybe thousands of papers people publish. Recreational papers, connections, and all kinds of things. They selected Wolfram Research, which is the founders of Mathematica software, a very reputable organization. They selected 8 papers. These days, about 10, 15. We're still there with 3, 4 papers. Cengiz's 2 papers were listed there as the original. That's what he meant, famous, okay? So story goes this way. And this is the book I was talking about. This is the normal science stuff, okay? So, but there is a little bit of touch, the kind of things I was doing. I kind of, the observer process, kind of stuff I slip in there. But essentially, it was a book. And Dr. Ye arranged a visit for me to Naval Postgraduate School, 1989. Richard Hemming is known to highly criticize mathematical books written about computers. See, the book is Fundamentals of Computing for Software Engineers. The original title was Fundamentals of Abstract Design, something or other. And the publisher says, no, Mathematical Foundations for Abstract Design. The publisher says, we cannot publish that title. Why? there's mathematical on the title. It won't feel good for computer science community. We should not have mathematical. Abstract design, no way, because nobody will know what abstract design is. With abstract design, I meant, hardware, software, all this stuff is the same stuff, really is, But I was trying to do an appropriate title. He says, who can use these things? I said, software engineering type of people to do research. He says, okay, let's put a software engineering title. So I put fundamentals of computing. Computing is essentially communication channel and all those things I'm going to show you in a moment, okay? And Chen is my master's student. He did one application, which is in the book. I asked him, because I don't want to type this old stuff that I already know. Typing, drawing diagrams, we'll be co-authors on this. You get half of the money. They gave money to us, actually, $10,000 or something, startup money, and they gave a computer. I gave the computer to him. And we finished the book, but I was worried that normal science people, although this is kind of normal science, too much math in it. So people kind of shy away, and Hemming criticized math books. So I want to see his approval when Dr. Ye arranged a visit to Naval Postgraduate School. Richard Hemming, founder of the coding theory. I visit with him. I asked 1 hour visit with him. He accepted. Not only that, he asked me to come every week. So Bernd was there too. Every week when he's there, I would go sit in and he would talk, I was just listening. He said, you know what? You don't have communication theory in your book. I said, what communication theory has anything to do with computing? I didn't know. But it put my critical thinking. I say, great, Hemming saying this. Then I recall my Collins days. In Collins Radio Company, which is the communication company monopoly in the United States, we were designing network operating systems and digital switches. Mr. Collins keep insisting that we're going to design as a communication channel. I say, it didn't make sense. The old man doesn't know what he's talking about, just like Einstein didn't know what he's talking about, or Collins didn't know what he's talking about. Don't use interrupts in your messages and stuff. So we designed the software, we were writing code, processor channel, a group of software called processor channel, another group of software called communication channel, another group of software called memory channel. These softwares, a bunch of firmwares and stuff too, combined together make the network operating system and other things, switches and stuff we were designing. I was just thinking these are just names. But when Hemming said this, I start thinking a little more detail, and then I start incorporating a communication theory into these things. And that's the end results. So actually, some creativity part, although I was kind of prepared by luck, started with this book's review by Hemming. So to make sure that big guys are convinced, I visit Einstein in London, in Wax Museum. So I asked him, briefly explain my theory. I asked him, what do you think about this theory? Oh, he liked it. He says, positive acceptance, that's the picture to prove you that we have that discussion. That's in the London Wax Museum, that's the picture. So what else proof you want? That's the picture, real picture. It's not Photoshop, it's a real picture. So I want to dedicate this presentation to two people, okay? One is O.D. Daniel. He was a PhD in mathematics, trying to get a PhD in computer science, because of better job opportunities and stuff. He was my classmate. In a class, one day, after I make a presentation about the finite state machines and things like that we studied those days, He come to me, he says, do you know about the N-Queen's problem? I said, no. Then he told me what the N-Queen's problem is. And therefore, I want to dedicate this to Daniel, because that problem was really interesting and play a strong role in, number one, solving the deadlock prevention problem. I use N-Queen's problem to solve the deadlock prevention problem for my PhD thesis, and I finished 77, completed 78, defended, and my professor liked it. You know, he was a theoretical physics guy, Dr. Udo Puch. He passed away last year. So I didn't know that problem, but I tried to solve the problem by hand. That day I couldn't. I go home and ask my wife. I say, she likes all kinds of problem-solving things. She said, do you know N-Queen's problem? She didn't know. She says, how does the queen move? She said. I said, I remind her how the queens move. So I put a chessboard. You know, less than half an hour later, she came, says, okay, here's it. I look at it. She really did solve the problem. And that made me determined, I'm going to understand this problem, you know. So that's what the story about that. The second person I want to dedicate is Dr. Rabinier, my grand mentor on many ways, you know, affected my life. You know, I work for his company. We design battle management systems. You know, I learned so much, you know, schooling after Mr. Collins. So I want to dedicate to him because year 2000 he came and I show him, we were doing some of the applications, you know, the Fourier series analysis of stuff, the Queen related stuff. I showed to him, he says, you can get a Nobel Prize with this. You can get a Nobel Prize with this, Dr. Ye said. I said, it's not in my, what is this, like a radar screen? You know, Nobel people, you know who gets Nobel Prizes? Those physics, you know, the chemistry, you know, I'm not counting the, you know, I'm kind of biased. You know, the soft sciences and stuff, they are good too, you know. Without them, we cannot be happy. But I am biased towards the hard sciences, physics. You know, in some ways, Linus Pauling, I guess, he said that, you know, what is it about these sciences? Either you do physics or stamp collecting. So if we're not doing physics, we're stamp collecting. So I'm kind of on the stamp collecting side. So it triggered my interest, just like Hemming, the communication. I said, what is this? I know Nobel Prize business. You know, then that's why I dedicate to it. Okay? So here is 1951, Einstein wrote. I read all his letters and stuff, you know, because one day, what changed my mind on Einstein was that I was doing these things. My polygons that I was working on wasn't closing. You know, polygon starts. It was not closing in my calculations. So I kind of want to represent planetary motions and stuff. But I know from textbooks that planets move as an ellipse, like you also know, right? Planets move as an ellipse. Anybody objects? In my meetings, I ask, nobody objects, because textbook says so. So I gave up. This is not going to apply there. I don't want to use it that way. A couple of years passed. I'm still angry about that. A couple of years passed. One day, Barnes & Noble, some unrelated book I'm looking at, it says, perihelion motion of Mercury. I had never heard of it. What the hell? Perihelion motion of Mercury? Well, it turns out that planets don't move as an ellipse. Textbooks are wrong. You have to read a book Einstein wrote, the Summary of Physics or the something like that for public. You know, very small book. It explains from A to Z all the way to quantum theory, okay, for public. And nobody reads, nobody cares. And also you can go to JPL, Jet Propulsion Library website. You could see how much the planet Mercury moves, it shifts. Mercury starts like this. doesn't come to the same place sideways. The distance is calculated by Einstein's general theory of relativity correctly. So shift is very, very small, but general theory predicts. That was like the hot water poured on my head. First time I said, this guy might be, I don't know, maybe he's right or something. Let me study. Okay? So start digging into relativistic motion in the sense of Einstein general theory of relativity. He really, if you study him carefully, he really didn't commit too much on relativity. He was trying to understand the fundamentals of particles. If he understands the fundamental of particles, he was going to solve other things. So 1951, look, 1951, Einstein writes to Bessel. When he finishes general theory, 1915, that's why we celebrate 100th year. 1915, he finished the general theory. 51, 4 years before he died, this is the letter he wrote. All the 50 years of conscious brooding we have taught brought me no closer to answer to the question, what are light quanta? He was wondering about light quanta. Then he says, of course today every rascal thinks he knows the answer, but he's deluding himself. Today, they say, every rascal thinks they know what photon is. Yeah, sometimes particle, sometimes wave, experimentally verified, and all kinds of things. But he wasn't convinced. There is a group of physicists think that maybe Einstein was thinking, some deeper things. Misquoted about God doesn't play dice, and his greatest achievement is relativity, stuff like that. They do the same thing with Newton. Textbooks, all these writings. Newton, what Newton said, that I stand on the shoulders of the giants. You hear everywhere. And then they say that Newton was praising previous people that he benefited from. Totally wrong. Newton was a Hook. Hook was very short, like a midget. And they were fighting. He wrote a note to Hook. He says, because they were disputing about the 1/r² thing, okay? So he wrote a note to him. He says, I guess I'm standing on the shoulders of the giants. He says, okay, you got it. See, it's quoted so wrong. Even Hawkins wrote a big book about standing on the shoulders of the giants. So it's just common science thing, the newspaper people and all those things. Nobody has time to dig into the details and stuff. Same with Einstein. The guy was trying to understand fundamentals. What are light quanta? 51, he didn't know. And he couldn't know. Okay, that's another thing. Because I can teach general relativity to elementary school kids. It's really straightforward, it turns out, as pointed out, okay? If you look certain ways, it's very, very simple. He has a piece of paper, geometry. He considers space as a geometrical space. He has the math for space. Then he has a particle, say, sun, empirically calculated outside. He takes this particle, which he hates, he writes, you should read, he hates. He puts this on this sheet of space, mathematically. Space bends. When it bends, creates space-time. That's his general theory of relativity. Everything accelerates the moment he puts this. Inherently, no acceleration on space. When he puts this, it becomes space-time. So space-time bends, planet Mercury moves certain ways, it just falls, and that's his essential idea. What he wanted to do, make a geometrical entity, make mass out of that. He tried, he couldn't do it. He could have crumbled this paper or space and becomes a mess, then pulls everything else, but he think about this, he wrote about this, he couldn't do it. So he gave up in around 1913, 12, if you read carefully, he gave up, he couldn't do this photon deal. He couldn't figure out the electron motions and things the way that he wanted to. Here is my speculation. This is up to here is a factual knowledge from the literature, okay? Now, I couldn't find some literature, maybe he wrote somewhere, his intentions, later historians can discover. I couldn't find it, but therefore I'm going to speculate. What he did is the following. He says, I couldn't figure out how the electron moves. Moves. See, these days it's kind of a nonsense, right? It moves. He says, if I relax the rules, I look at the particles in space, the ratio of the sun to Mercury, and he also knows that this discrepancy in Mercury cannot be solved by perturbation theories, the other planets' effects, everything. Nobody was able to explain in his time that distance. So he says, why don't I use this with my theory? Sun and Mercury, just like, like in the old days, they used to think nucleus and electron, okay? Well, I cannot do with nucleus and electron. Let me try Sun and Mercury. Because Mercury moves, although they think that continuous, it's not. From quantum mechanical point of view, it jumps like this. It's a polygon, really. And so Mercury, but at the time, Mercury comes like this. It doesn't touch, right? Go this much. So he says, maybe I can make this calculation. Let me do the reverse. Take the sun, make the sun heavier or massive. Could be big, small, but massive, okay? Massive sun, leave the Mercury alone. What happens? Sun pulls Mercury. Pulls. Again, I'm thinking Newtonian, okay? Excuse me momentarily. So, if Mercury, the sun is so heavy and so massive, Mercury will be like an apple. Meaning, throw the apple, falls back. So Mercury will go on sun. Let's relax the mass a little bit. Now Mercury comes, instead of hitting the sun, it goes like this. But cannot go far because of this pull. Comes and hold again. Pull again. Hold again. Pull again. That's what Mercury moved. That's what he was thinking. He says, this pull is too strong in the nucleus and electron system, and this is almost like a smear, energy smear. It's not like, he also mentioned, you have to read. He says, speed of light, he chose c. Inside the atom, speed of light is still c, but it is faster than the light outside. Hey, he wrote about this. Because of that's why atom is neutral. That's why when you apply classical mechanics, they say, electrons don't move like Bohr model around atom. Why? Because if it does, that will, based on our equations, it's gonna show energy dissipation. It doesn't, neutral, therefore doesn't. I wasn't thinking that way. So my speculation is the relativity theory, he go to the space to understand the atomic structure. That was his passion. And why? Because of this. Where is the pointer? Because of this. You see, He was trying to understand electromagnetic theory. He was trying to understand electron physics. He was trying to understand atom. He was trying to understand molecule, other substances, and life forms. That's what he was trying to do, with a fundamental understanding of basic material, photon. That's what he was trying to do, because he's smart enough not to trust people, even Grand Maxwell that he study and respect. You see, here, you know what we do? We teach people today in electromagnetic flux, I do. We say electromagnetic spectrum, heat is here. Heat is totally disorganized system. And then when we become electromagnetic waves, radio waves, then organization starts. And once the organization starts, Maxwell theory kicks in here. And when we reach the gamma rays, Maxwell theory ends. You know what we teach in class? We say electromagnetic spectrum starts with radio waves and with gamma rays. Then God asks, how come? No, I didn't do it that way. This God did this way to confuse people? Einstein knows that. Electromagnetic spectrum doesn't end. Maxwell theory ends. See, that's not the way we teach. We say electromagnetic theory ends. Well, if you manipulate electromagnetic theory, which he was trying to do, Einstein was trying to extend the electromagnetic theory the way it is done beyond to cover the electron and atom. He couldn't do it. That's all this relativity business and all these things, the Lorentz transformations, stuff like that. Because of that, that's his passion. This was hard because the paradigm he's operating is a very, very restricted mathematics. You know, the projective geometry, space plus time. You know, Minkowski introduced space-time. Once he realized space-time is useful, in the beginning he rejected. He says, forget the space-time. These mathematicians complicate things, he said. But then he realized that, oh, it's useful. So he used space-time. I don't use space-time. I use space frequency. That's that space that Einstein has, separate the space, outside mass. When he puts it, he creates space-time artificially. He hates that. So if you have a space frequency, which means, just like Einstein envisioned, this piece of sheet, which is space, every point vibrates, accelerates actually, not vibrates, accelerates. Besides, acceleration has direction. Direction means you can incorporate second law of thermodynamics and everything else, which today's theories don't. That's why in the particle theories and wave theories, you put t replaced with minus t goes backward and forward, and everybody else stated, like said, you go visit your grandfather, stuff like that. And Gödel showed that nonsense to Einstein himself. Look at this. So we'll get to that. But that's what he was trying to show. Now, he asked, what are light quanta? I say, they are communication channel systems. This is your light quanta. Light is like that. It can be a particle too. When this system actually projects itself as the wave forms, or after a certain angle, I'll show you, it exhibits like a particle. Because if energy increase, let's do some silly example, okay? This finger, I'm moving like this. You're seeing that it's moving back and forth, increase, still moving, increase, and then with your eyes, no more you could see. You say, it looks like a stick. Then you say, it's a stick. Then I say, don't trust your eye. Do something else. Send here some kind of a wave. Some high frequency wave. I'm doing this. It's so fast, your eye thinks it's a stick. You send the high frequency wave, passes through. He says, oh, it wasn't a stick. It was something else. And then eventually, like various experiments done in atom, depends on the frequency that you send, it bounces back. It bounces, it's really not, but Feynman says it's not, it doesn't. So we pretend it's bouncing back, and then we do some mathematics associated with it. This deal, when the wings get closer and closer after a certain angle, start exhibiting particle behavior. And when it interacts with other particles, space-time entities, it modifies itself continuously. In other words, not only biological systems, slow cooking, like every one of us, slow cooking, we're getting older and older. Every yeah, 10 minutes. I thought 4 hours, so have. Every non-living material also partitions. You know, second law of thermodynamics says that. Partition function, essentially, a little more generalized way of looking at the second law of thermodynamics. Everything partitions, you know, we gave different names. He was born, he kind of a baby growing up, yeah, partitioning. He get a teenager, further partitioning, and you know, partitioning, and the partitioning accelerates because that's why it's not coincidence that entropy is x log x, a function of the logarithmic first moment of the logarithmic function. It is not a coincidence. This is the kind of math. Combinatorial mathematics is the way to go. We can make all kinds of fictions in math. The math is beautiful poetry. It's not physics. To apply mathematics to physics, we have to somewhat modify math from the physics point of view. Take number line. You take a number line, you say, you know, Cantor proved beautiful theorems. Between 0 and 1, there are more points than the natural numbers. Well, mathematician says so, and it is consistent. Well, ask physics guys, Mr. Planck. Planck says no energy can be longer than Planck length. So if no energy can be longer than Planck length, why my number line distances is more than Planck length? I mean, smaller than Planck length. It's nonsense. So, from the physical point of view, a lot of the mathematics is nonsense. And negation, again, the trick that our brain tells us to survive, it works beautifully in math. It doesn't work in physics. You know, I play the game with my students. I say, I sit on a chair. I say, what am I doing? They say, you're sitting on the chair. What does sitting means, I say. You know, we sit. My pants sitting and touching? He says, touching? Okay. What is touching? And I heard from somewhere that there are electrons moving around the atoms, pants made of atoms, seat made of atoms, the electrons moving, so am I touching anything or floating? See, physics, different than everyday math and everyday logic. So don't trust your eyes. It is three-dimensional space. It is creation of our brain. Many neurologists already accept that. And of course, time is fiction of our mind. But space frequency rooted in the mathematics. If we want to understand, you see, for example, that figure, previous figure. If you want to make a particle out of it, take an inverse Fourier transform. You see a particle. You take this thing, make an inverse Fourier. It looks like a particle. Because then we can make sense. We don't make sense to this because it's the complex space frequency. Space frequency complex domain, our brain cannot grasp. Okay? So this is the kind of meta I use. Here's a couple of terms. Here's the heart of it, is this the polygon. That's the way Einstein was thinking. These polygons actually communication channels. You can take a communication channel, which is probabilistic, assign a Fourier transform each line, and that's why the Fourier transform is here, and then attach some quantum numbers on it, and all of a sudden you have some interesting things. See, this is comes here, attached to quantum numbers. This is actually the shell structure of atom. We apply to represent the atomic shell structure, which is energy structure, using this line of thinking, first time, information theoretical representation of the atom shell structure. Currently, physics explain these things in a different way. Actually, kind of messy, a little bit of Newtonian, a little bit of quantum, that kind of thing. No grassroots from first principles. They don't explain with first principles. This does. Actually, that simple thing looks like, in reality, is this. This is the matrix. I call it U matrix. See, this term is interesting here, non-stationary. Non-stationary means inherently changing. Airplane is a very complicated device, but it is stationary internally, meaning that, I mean, in reality, even that is not stationary. Well, let's forget that part, okay? The airplane is flying. I can dynamically analyze. Airplane is here. I can calculate dynamic motion. The way to calculate dynamic motion, there is a matrix, state-space matrix. You take a previous state, multiply with that, and get the next state. So I can take the state-space matrix dynamics of the airplane. Initial positions, parameter of interest. I choose some parameter of interest, let's say height and weight and the speed and the rotation in the engine. I choose it, okay? And then here's the airplane. The next state is here's the airplane. Next state. But airplane itself, assume not change. Biological systems, you cannot do that. You take a frog, broken to pieces, put it together. Try it. You take an airplane, broken to pieces, put it together, still an airplane. Frog, still not a frog anymore. Broken to pieces. Non-stationary processes, the way heart works, body works, living organisms, non-stationary. In my opinion, this is the only non-stationary state-space matrix. That's also, wrong. Every theory is wrong, even quantum theory. Even this theory will be wrong at one point. Unitary matrices. There is a rule that unitary, because invertibility is necessary in current quantum physics. This is not unitary, because this is non-stationary. I can make it unitary. What I can do, I can modify these parameters slightly, and then I can turn into a Markov process or any other kind of structure, just choosing certain parameters. I can make it invertible. But as it stands, not invertible because I didn't make it. It accidentally occurred. You know how this accident occurred? This is how. I was looking at these communication channels connecting with the Fourier series. Then I noticed that these three quantum numbers match this structure. So I put these quantum numbers, envisioning that, let's look at the atoms from the hydrogen, helium, and all that, these electrons building on top of it like this. I start thinking and start putting this little bit try and error. I still have the notes. And then, as a result, this came out. Then, when this came out, this is like 1994, 95. Then, I remember Richard Feynman. Feynman says, you are the easiest person to fool. So I said, I'm fooling myself. This is not possible. So I start studying since 1995, what the hell this stuff is? And try apply and stuff, and eventually the atomic structures and all that. So it started making sense after 20 years. And this is currently polarization and the electromagnetic theory works. Electromagnetic theory, electric field, magnetic field, and the wave propagation goes this way in a cylindrical fashion. Remember I told you electromagnetic theory ends for some reason? The reason it ends because currently it is cylindrical. It's not. Wave propagates like this, slightly bends, a little bit up. So it's really supposed to be cone. If you keep it this way, this is an approximation. That's why it fails in the gamma ray. If you want to extend in gamma ray, instead of the cylindrical motion, you have to have a motion like a cone. Like this. You know, believe it or not, the whole universe is like this, as Einstein envisioned. All structures have the same shape. And to analyze it, this is the channel. And let me go to the next one. Okay. This is chessboard. This chessboard. This is the communication channel of Shannon. Shannon attaches probabilities on these things. Instead of probabilities, we put Fourier series. So it could be instead of, I can make it probability, it's no big deal to make the probability special case. Shannon becomes special case. But here, actually, since this is a Fourier series, it becomes, structured like this, it becomes a vibrating system. And that vibrating system is looking at this cone from top. So to analyze the cone, you take a slices, like MRI does. A slice, analyze the vibration. Another slice, another. Slice after slice after slice. So this slice is actually top view of that cone. Next slice, and next slice, and next slice. And all these slices interfere with each other, quantum entangled fashion, and make this unique representation of space-time cone came out of it. I didn't do it. It just came. And when I saw it, I said, something's wrong. I'm fooling myself, Feynman style, okay? So this takes me back to the least action, the Ancueus problem. There is a very famous theorem by Shannon. Shannon says that you can send only noisy messages, but noisy messages can be controlled. But you can never send noiseless message. So it turns out that that theorem is equivalent least action principle presented by Lagrange. You know, Lagrangian, you take an integral, and Richard Feynman used that. I extended his theory, by the way. I didn't mention here, but quantum electrodynamics, that's what it is. I took quantum electrodynamics with these ideas, extended quantum electrodynamics. He had the right idea. He was looking combinatorics, but the Feynman's mistake, as usual, was the time. He got a clock. I don't have a clock. Clock is the space-time itself. Clock is right here. You see? This is vibration. That means time already here. You don't need time, you know? Once you have frequency, you don't need time. If you want to see the time, you just inverse transform, you see the time, okay? So this is the side view. This is the top view of that structure. Okay, a few more minutes, you know, here. Current theories are particle behavior, all the theories in the world, either particle behavior or wave behavior, nothing else. If I tell somebody, bring all the published books, scientific books, pile it here, and categorize. You can only categorize two ways. Particle way of doing calculation, wave doing calculation. Some quantum guys will say, hey, you know, something is wrong. In quantum, we do particle and wave. Fine. Take your quantum books, take the particle parts, throw here, wave parts, throw here. You still have two piles. Humanity generated only two original ideas since the beginning. Only two original ideas, which is particle models, you know, and the wave models. Nothing else. Einstein said that scientific theories is the refinement of everyday ideas. A naive everyday idea is things move. That's naive. Everybody thinks things move. Everybody sees it, everybody perceives it, so things move. That's the naive worldview. That is worldview articulated by Galileo, Newton, and Einstein, push to relativistic things move deal, okay? And when they couldn't do things with things move for light, Faraday comes in. Faraday, and then field theories and stuff. Maxwell put some mathematics on it, and Einstein put the relativity. Couldn't push to Maxwell further. Feynman comes in, he says, wait a minute, Mr. Einstein, I'm gonna study deeper for your case, okay? Of course, in between there is Lagrange and Hamilton. I don't have time for these guys, okay? Since Einstein says all scientific theories is the refinement of everyday idea, these days there is another everyday idea, communication. If I can make communication mathematical enough, like these big guys do here, other big guys do here, then all of a sudden we're going to look everything as a communication systems. Okay, I tell my students sometimes, you know, these three guys sitting in the heavens, and Shannon understood the way we treat his theory. Shannon is sitting there, and of course Maxwell, and of course Einstein and Newton. And this is the conversation goes in heavens. They say, I threw a ball into somebody's body. They ask Newton, Mr. Newton, can you explain this? He says, no problem, energy, equations, and things. They ask Maxwell, can you explain this? Maxwell says, no, it's not my territory. That's a particle moving. I don't care. And then Einstein, same way, supporting Maxwell. And then the next time, they zap with some kind of X-ray. They say, Mr. Newton, can you explain this? He says, no, it's not my area. It's not a particle, it's a wave. Then Maxwell explains, Einstein supports. They ask, this is our guy, Shannon. But Shannon now knows space frequencies and things like that. He learned attentions to his thing. Okay, QED a little bit. Can you explain the ball thrown to the sky? Shannon says, yeah, no problem. Energy transferred. And here is the massive hole it made, but also transfer information. I can give you that too. Not only a big hole there, also other things. How about X-ray doing? Shannon says, yeah, I can do that too. Well, all you did, transfer energy, again, in a structured way. That structure interfered with the other structure and entangled and create a new structure. Here's the new information for you. It gives the information plus the damage caused by the X-ray. So Shannon was doing better in heaven. Final thoughts. Einstein commented to his Nobel laureate Stern, I have taught 100 times much more about the quantum problems as I have about relativity theory. He wasn't concerned about relativity theory. Everybody thinks he didn't even get a Nobel Prize for relativity, okay? So he want to extend Maxwell theories, which he did with relativity. Today, in our classes, we use relativistic Maxwell equations for short distances because otherwise Maxwell equations don't work. This is for special theory. General theory is not integrated any part of the particles or physics. End of story. It's there. General theory is a shining star. All physicists go there, look at it, they pray for it, they say, oh, this is great, Einstein is great, general relativity great. Oh, it's too complicated, you don't understand, kind of things to general theory, but it was not incorporated into current physics. That's why it's out there. Second law of thermodynamics is not inherently integrated into particle or wave theories either, because second law of thermodynamics has directionality. Things go in one way. All physics equations, from quantum invertible matrices down to particles and wave theories, they all reversible time, reversible things. You take t, replace with minus t, it goes forward and backward. Is it correct? Yes, of course, at some level it's correct. At some level that planets move as an ellipse, yeah, it's correct. If planets move as an ellipse, I accept. But they don't. Next thing he says, in response to a query from Sommerfeld, this is later years actually, Einstein states that relativity theory does not at all provide definitive theory of electrons. Today everybody knows this, every rascal knows. A physical theory, look at this, watch that one. A physical theory can be satisfactory only when it builds up structures from elementary foundations. To the day he died, he could not discover elementary foundations of his theory. He really hated it. And many, many writings he displays, and his close friends, letters to close friends and everything. That's the reason he resisted the quantum physics. He built the quantum physics. He's not against quantum physics. He is only against the Copenhagen interpretation of it. Oh, by the way, in that cone in the middle, it's just actually circle is a Planck length. Surroundings of the circle is Planck length. And next is structure is. Our theory assumes only elementary foundations. Einstein gave the insight. Everything I told you, he already really see it. I didn't add anything. It was there, it was written. I just add some math. That's it. And math is so trivially simple that you can show undergraduate students, they will appreciate. That's very simple math. Has no complicated general theories, all these projective geometries in space, stuff like that. But you have to know a little bit about Riemann surface. Riemann surfaces, you take a complex plane, rotate the complex plane. You can make two planes. Mathematicians do. I can't. I'm looking from the physics point of view. When you take this one piece of material, which is first law of thermodynamics, mathematician says, one piece, they rotate, the second piece gets smaller. He says, yeah, make it bigger so that it should be consistent. That's what Riemann surface is. I don't. When I rotate, second piece gets smaller, and next piece gets smaller and smaller and smaller. That's why cone occurs. It's actually, this is really a Riemann surface in a really modified way, okay? So I accept the first law. I accept the second law of thermodynamics, which is everything partitions continuously. You're not same from morning to day. Everything, and this material is not same. Everything deteriorates continuously. It's just a matter of time. Everything is gonna fully deteriorate. Accelerated framework of general relativity, which means space frequency math. So I assume he says everything accelerates, and everything accelerates slightly differently. That's the clock differences. So in this sheet of space frequency sheet that first law says, every point vibrates in a different way. Or vibrates is an old word, Maxwell, because it is the communication channel noiseless. We cannot have it, second law prohibits. So it's not really vibrates, it accelerates. What is acceleration? In a polygon, this distance, next distance bigger, next distance bigger, 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 that kind of stuff, okay? And this is in the complex domain. But I want to understand, this is complex numbers we don't understand. I want to understand this in my brain, not in math. That's easy. You take this, make an inverse transformation to a Fourier system, you see a sphere. So, in the old days, they say Earth is flat. Okay, when you say, is it really? Then some people object. No, it's not flat. Then they told them, are you blind? Look around you, it's flat. You know what we say these days? Earth is round. If anybody objects, go to space, look. It's round. Well, I have a news for them. It's not round. It's space-time. Earth energy system is like this. But if you want to see with your eyes, you will see like round, yes. But if you want to make precise calculations, that's the way you have to do it. How the photons coming, all these electromagnetic fields and stuff like that. High precision calculations, the moon is moving certain rate, and the planets perturbating certain rates. If you want to do highest possible precision, then you have to do the calculations in space frequency domain. And that's the domain. Then if you want to visualize with your eyes, like we do in electrical engineering. Electrical engineering, we do all our calculations in frequency domain. We call it a technique. Technique, not fundamental, technique. And then if you want to see what the voltage is and the frequencies, we do an inverse transformation, then we plot, okay, this is the way it is. That's what we understand. Let me explain, speculate now. From theory, I'm moving speculation. One more minute, okay? Unsolved problems of today. Some cosmological problems. They say that big galaxies are moving away faster and faster and faster. And no explanation. I say, okay, let's explain that with this. Okay, you see, since everything has this form, this is where we are. Our observation point is, let's say our galaxy is here. From our galaxy, and relativistically, we can only see this way. Bernd demonstrated it already. This is the way, this is the cone. Well, difference is that a space frequency cone versus space-time cone, pretty close to each other, actually. So when I can see that way only, I cannot see that way. What if we accept accelerated framework of general relativity? Everything is accelerating. So this galaxy is accelerating also, this way. Well, since I cannot see things accelerating faster than me, I cannot see that way. I can only see things accelerating slower than me, which means coming behind me, slower rate. You are in a car, this car, you're looking from a hole, bunch of cars coming from behind you. You're going 60 miles an hour, slowly accelerating 65, 66. And next guy coming 40 miles an hour, slowly accelerating. And next guy coming 20 miles an hour. You're only seeing that way. What would you see? You don't notice anything. Oh, this guy is going away from me with 20 miles an hour. And that guy is even faster, like 40 miles an hour going away from me. That's what we are seeing now. You know, once you adopt this worldview, which is consistent with first law, second law, and the accelerated framework, nothing else. You don't need to assume Newton, Maxwell, Einstein, nothing except the framework of Einstein, not his space plus time mathematics, okay? Then you can explain a whole bunch of other things, you know, electromotion. You can map to Schrödinger equations, Feynman partial reflection. You know, partial reflection is window. You look at from window, you see outside, but you also see part of your face. How come? That's partial reflection. Because of this guy, partly outside, partly in, then you could see partial reflection. Feynman already explained that, but it's more systematically can be explained this way. Richard Feynman's quantum electrodynamics. Questions? Let's see if Einstein asks questions. I wish he was here. I think he will enjoy it. No questions? You're tired? You want to go lunch? It's not even 4 hours, guys. I can give this talk in 15 minutes, which I choose not to. 1 hour, 4 hours, 4 days, 40 days. You know, depends on which level you want. And you're welcome to ask questions later. Any level, any angle, anything. All these muons, all these particles, stuff that you read everywhere. Come and ask me if we can explain. Take care.